Now I would like to click on this file. I would like to select this new option. So you can see this is the default stack layer. And now I am going to create a device structure that will consist of gold anode, calcium cathode, and a MES PPB layer that will act as a semiconducting region. So here first you can define the layer structure, their thickness, and then you can enable the module. So you can see this is the advanced optics module. This is the absorption module that will required for the solar cell simulation. This is the drip diffusion module that will do required for the electrical property simulation. This is the emission module that will require for the OLED simulation. So here we would like to define this emission module and this drip diffusion module. Now you can see this emission setting tab has been enabled and this drip diffusion setting tab has been enabled. So once you enable the module, then you can go to this layer structure. And if you want to add more layer, then you can click on this add layer option. Now you can see this is our surrounding layer. Here we can define the gold layer that will act as a top electrode. So this is the gold layer and we can define their thickness. So here I would like to define the thickness 10 nanometer. Then select this third layer. And here I would like to define MEH PPB layer. And you can also define their thickness. So for this layer, I would like to define their thickness 120 nanometer. And here I would like to define calcium that will act as a bottom layer. Also, we can define their thickness 10 nanometer. And here you can see this is the layer structure. This is our surrounding incoherent layer. This is our gold. This is our gold 10 nanometer. This is our MES PPB layer 120 nanometer. And this is the calcium 10 nanometer. So this is the surrounding and this is the substrate that will act as an incoherent layer. So once you define the layer name and their thickness, then you need to import their refractive index. So either you can define the constant refractive index constant birefringence, and also you can import the file. So first you can select the layer. Like you can see this gold layer has been selected. And then you can define the refractive index. So here I would like to define, you can see this is the constant refractive index 1.75. And this is my calcium. And their refractive index is, real part is 1. And if you want to set the electrical properties of this CMES PPV layer, first we can set as a semiconducting layer. So this is my semiconducting layer. We need to select this gold as an electrode. So this is my top electrode. And then you can define their boundary condition. Like you can see, this is the ohmic boundary condition, and this is the thermonic boundary condition. So you can see this is the ohmic boundary condition, and this is the thermonic boundary condition. So this thermonic boundary condition has been selected. Also, you can define their work function. So you can define the work function for the gold electrode in the unit of electron volt. So I would like to define 5.1 electron volt work function for this gold electrode. Again, I would like to select this calcium layer. Here you can select this electrode. So this is your top electrode gold, and this is your bottom electrode calcium. And this is our semiconducting layer. So in the same way, you can define their boundary condition and their work function. So this is the thermonic boundary condition. And here I would like to select 3.3 electron volt work function for the calcium layer. Again, you can select this CMES PPV, and this layer you can select as a semiconducting layer. Now you can see this semiconducting has been enabled. And you can select this semiconducting tab. And here you can import the electrical properties. So electrical material you can import from our database. Like this is the import option. And you can see this is the electrical material database.em file. So you can see this is the MES ppb dot em file. You can select this open. Now you can see the electrical material has been selected. And if you want to show the script, you can see this is the electrical material that I am imported from my local database. You can see the field temperature dependent mobility model has been enabled. This is the energy level, luma and HOMO value. This is the epsilon value for the holes and electrons. This is the optical charge generation. You can see this is the constant mobility model for the electrons and holes. This is the field dependent mobility model and their value. This is the field temperature dependent mobility model and their value that has been defined. Like you can see, this is the EGDM, ECDM, and this is the excitons. You can see this is the trap. So you can see this is the charge parameter. Like here you can define the HOMO and LUMO value. You can define the dielectric constant value. And if you want to enable the doping, so like acceptor doping, donor doping, you need to enable. And here you can enter the value. So this is the acceptor doping. This is the donor doping. You can see this is the optical generation efficiency. You can see this is the mobility model. This is the field temperature dependent mobility model. This is the constant mobility model, field dependent mobility model, field temperature dependent mobility model, EGDM, ECDM, and this is the field dependent mobility file. So this is the mobility model that user can select. So this is the charge parameter. You can see this is the excitons parameter. So if you want to enable the excitons, here you can see, you can click on this add option. Then the excitons tab will be enabled. So here you can define that generation efficiency, diffusion constant, saturation limit. So this is the excitons parameter. This is the traps parameter. You can enable the trapping for the materials. You can see this trapping has been enabled. You can also enable the SRS recombination and trap recombination. You can also enable. So this is the traps. This is the mobile ions. You can see this is the mobility model, constant mobility model, static mobility model, field dependent mobility model, and field temperature dependent mobility model for the anions, and the similar for the cations. You can see this is the recombination. So once you enable this semiconducting, then this tab will be enabled. Here you can see our emitting layer is not defined. So we can select the CMES PPV and we can select as a emitter. Here you need to import their luminescence spectrum file. Now you can see the file has been enabled. So by clicking this option, you can also enable or disable the emission module, emitter layer. Now you can go to this drip diffusion setting. So you can see this is our semiconducting layer. Select this drip diffusion setting. And here you can see this is the drip diffusion mode. Like this is the steady state mode. This is the transient. This is the AC impedance. And this is the intensity modulated photocurrent spectroscopy. And this is the intensity modulated voltage spectroscopy. So I would like to select this transient module, transient mode. And then go to this transient signal. So here I would like to define the pulse squared signal. So just you can enable this transient voltage and here you can define your signal. So here I would like to define the pulse squared signal. So I can define 3 pulse signal and then you can define their value. You can define their voltage and their time duration. Now you can see this is our first segment. Here we can define the 0 voltage. You can select this first constant. Here I would like to define the 0 voltage and their time duration 50 microsecond. Again, I would like to select this constant. And here I would like to define 4 voltage. 4 volt I can define. And then I can define the time duration 100 microsecond. So here I have defined the 0 voltage. Here I have defined the 4 voltage. And here I would like to define 0 volt. Then I would like to define their duration, time duration, 150 microsecond. So in this steady state, I would like to define this custom, and here I would like to define from 0 volt. Now this drip diffusion mode has been selected. See the transient mode. So here you can see this is the general settings, and this trapping has been enabled. You can also enable the electrical circuits like RLC component, like series resistance, parallel capacitance, and lateral resistance. And then you can define their value. So this is the general tab. This is the steady state solver. This is the transient signal you can define. You can define their voltage and temperature range. Here you can see this is the transient solver. Now you can go for the simulation. So here you can enter the project name. And then you can select this run option to run this job. Now you can see this transient solver project has been simulated. You can see this is a transient, and these are the graph. So like you can see, this is the applied voltage transient. We have defined the voltage and their time duration in the unit of microsecond. You can see this is the current graph. This is the current transient. And this is the current versus voltage graph. Here you can see this is the device component, device current component. And this is the power density. This is the power density versus voltage graph. So these are the transient spectrum. And if you want to calculate the IV curve, current voltage curve, then you can select this sweeping. You need to enable this sweeping mode. And here you can sweep the voltage. So you can select this elliptical. So for the IV curve, first we need to go to this depth diffusion setting. And here we can select the steady state mode. Now you can see this is the steady state mode. And this is the steady state solver. Then you can go to this sweeping. You can enable this sweeping. And here you can select this voltage. And then you can define the range. So here you can select the parameter voltage. Then you can define the range. Like if you want to shift the voltage from 10 nanometer, 10 volt to 100 volt, then you can define the step size. Like if you want to define here 5 volt, then you can run this simulation. Now you can see this voltage sweeping has been enabled. Then you can select this run option to run this job. Now you can see this is the device current component. You can see this is the current graph. This is the power density. Also, you can see this band diagram. You can see this is our gold top electrode. This is our calcium bottom electrode, and this is our semiconducting region. You can also zoom this semiconducting layer, and you can see this is the voltage that I have defined. And then you can show the changes from 10 voltage to 100 voltage in the step size of 5 volt. So this is the band diagram. This is the charge density. This is the current. Here you can see this is the electric field, and this is the mobility. Here you can see this is the mobility for the holes, and this is the mobility for the electrons. You can see this is the mobility for the electrons. And this is the mobility for the holes. So this is the potential. And you can see this is the recombination. So by enabling this module, you can calculate various property either for the solar cell and OLEDs. So in this session, I showed like first I have showed like the organic light emitting diode, device structure and their emission spectrum. And this is the electronics, organic light emitting diode and their simulation. And you can see this is the result. You can see this is the emission spectrum project file into the glass layer. This is the emission spectrum into the air layer. And this is the electronics OLED simulation. Either you can see multiple example are there. So this is the existing example. You can see this is the full OLED example folder. You can see this is our glass layer. This is the ITO layer that will act as a top electrode. This aluminum will act as a bottom electrode. This is our whole transport layer. This is the electron transport layer. And this is the emission layer. So these are the semiconducting region. And this is our electrode. Here you can see this emission setting has been enabled. You can see this is the emission mode, spectral, dissipation power analysis, and mode analysis. You can see this is the layer structure, graphical representation. These are the incoherent layer. In between the glass and air, these are the coherent layer. And also you can see this is the energy level diagram. This is the drift diffusion setting. So in the mode you can see steady state mode has been selected. So that we can get the IV curve. You can also select this transient mode. In the sweep setting you can see we have enabled the parameter emission angle. And if you want to run this job, you can select this run option to run this job. Now you can see the simulation is running. And you can see this is the electrical profile output data. And this is the emissive properties output data. Also you can see this is the optoelectronics output data. Like this is the generated photons. And this is the spectral output data. So these are the absorptance, reflectance, and transmittance. You can see this is the spectral emission output data. Like this is the emission spectrum. This is the normalized emission. And this is the white emission. So if you want to show the electrical properties, like this is the device current component. You can see this is the excitones. This is the excitone rate. And this is the internal quantum efficiency. So whenever you define the accurate parameter, then you will get the exact result. can see this is the CIE color diagram. So for the OLED simulation, this emission module need to be enabled, and for solar cell application, this absorption module need to be enabled. You can also you can also simulate tandem solar cell, perovskite based solar cell. Like you can see, these are the various examples. Like you can see, this is the perovskite IV curve, and this is the perovskite LED. Here you can see this emission setting has been enabled for the LED simulation. You can see this is the perovskite layer that will act as a emitter layer. So for the perovskite based LED, we have first defined the air top, air bottom, in between the coherent layer. Like this is the glass layer, this is the ITO layer. You can see their refractive index material database and material file. So multiple layer has been created and their thickness has been defined. You can see this is the layer structure information. This is the emission setting. You can see this is the sweep setting. We have defined the emission angle. And if you want to run this project, you can click on this run option. Now you can see the simulation has been completed. And this is the spectral graph. Like this is the absorptance spectrum. This is the reflectance. This is the reflectance for the holes. And this is the transmittance. Also, you can see this is the spectral emission. And you can see this is the current efficiency. So this is basically a perovskite based LED. So this is the LED simulation. So if you want to create a solar cell simulation, you need to enable this solar cell absorption module. You need to disable this emission module. So for solar cell application, this absorption module need to be enabled. Like if you want to create a new file. So for solar cell simulation, you need to enable this absorption module, and then you can define their layer structure and their thickness value. So for the optical property simulation, you can enable this absorption module, and for the optical and electrical property calculation, you can enable this absorption module and drift diffusion module. So for electrical and optical, both module need to be enabled. Like if you want to simulate any solar cell for the optical properties, so first you can define their layer structure. Like you can see here, I would like to define the air. This is our air top layer. Here you can create multiple layer by selecting this add layer option. So if you want to define the glass layer, like you can see, this is the glass. So this is the glass layer. So as per your need, you can define the layer structure, their thickness. You can import the refractive index material file. Either you can create a new one, either you can import from our database. Like here you can see, this is the ITO layer. Here if you want to define P dot layer, so you can see this is the P dot layer. You can see this is the P3ST PCBM layer. And here I would like to define aluminum layer. And this is our air bottom. So once you define the layer name, you can define their thickness. Like you can see, this is the 100 nanometer for the glass. Here I would like to define 125 nanometer. So this is the P dot layer and their thickness is 50 nanometer. You can see this is the layer structure. This is the P3ST PCBM, 100 nanometer thickness. This is the aluminum. And here I would like to define 500 nanometer. So this is incoherent air top and air bottom, and these are the coherent layer. So once you define the layer name and their thickness, then you can import their refractive index material file. So either you can define the constant refractive index, like you can see this is the glass, and their refractive index constant 1.75 for the real part. So you can select this ITO layer. You can select this file. So either you can create a new file, either you can import from our database. So this is the existing database. And here you can see this is the ito.nk file where we have defined the real and imaginary part. Here you can see these are the wavelengths. This is the real part and this is the imaginary part. So this is the ITO layer. Similarly, you can import their refractive index file for the P dot layer, P3ST PCBM layer, and aluminum layer. Like you can see, this is the refractive index material file for this aluminum layer. Similarly, you can import the refractive index file for the P3ST PCBM layer. Here you can search P3ST PCBM.ank file. And then you can select this open. And now you can see this is the graphical representation, real and imaginary part. Similarly, you can select this P dot layer and then import their refractive index material file. Here you can search P dot refractive index material file. So this is the P dot material file. And you can select this glass layer as an incoherent layer. From this general option, you can enable either the incoherent layer, transparent layer, isotropic layer, scattering layer, and emitter layer. Like this is the incoherent layer. Now you can see the layer name, thickness, refractive index material file has been imported. Now you can go to this absorption setting. And here you can define the range. Wavelength range you can define. And also you can see this is the spectrum file. So this is the sun spectrum. Here you can see this is the intensity and this is the wavelength. So this is the sun spectrum. And then you can go for the simulation. So once the simulation will be completed, you will get the output folder. You can see this is the result tab. And this is the spectral. So like this is the adjourtance. This is the layer adjourtance for this solar cell. For this structure. And this is the reflectance. This is the stack contribution. You can see this is the glass layer. This is the IDO layer. This is the P dot layer. This is the P3ST PCBM layer. This is the aluminum. And this is the reflected color. And for the IV curve, you need to enable this drift diffusion setting. You can define the electrode and semiconducting region. So whenever you define the drift diffusion setting, then you will get the electrical properties. So for the electrical and optical properties, absorption setting, absorption module and drip diffusion module need to be enabled. Now, if anyone has any query regarding either solar cell, either OLED simulation, then you can unmute your mic and ask me the question. So whatever the questions you have, so you can ask, so that I will try to help you.
Hi, this is Vishal. So you are taking the layer, downside layer, air bottom, 100 nanometer. Why this is so? If someone has both sides glass, like if both side absorption, then what will we do?
Yes, sir. So, sir, basically solar cell is surrounded by the air, so that we have created the air top and air bottom layer. So if you want
If
to, yes,
Yeah, if you want to add the glass on bottom as well and two side absorption, like front and top bottom, that is the rear side as well and front side as well. So that structure can be designed, right?
yes, you can design.